Hello students, welcome to lecture 3 of the ongoing chapter Photochemistry. Here we will continue from our last lecture and discuss the photochemical reaction between hydrogen and bromine, the photodissociation of hydrogen iodide, and try to comprehend the Jablonski diagram. In the last two lectures we have seen what photochemistry is and how presence of light is a prerequisite for the photochemical reaction to take place. Light of a particular frequency, say nu, and energy h nu, can excite a molecule in the ground state to its excited state so that it can finally form the products. Let us look into the photochemical reaction between hydrogen and bromine. The mechanism for photochemical reaction between bromine and hydrogen follows the same kinetic law as the thermal counterpart. In presence of light, h nu, the bromine molecule decomposes to give two atoms of bromine. One of that atom reacts with the hydrogen molecule to give hydrogen bromide and one hydrogen atom is liberated. This liberated hydrogen atom then reacts with the bromine molecule as well as the product hydrogen bromide to finally give the bromine atom, the product hydrogen bromide and hydrogen molecule. The bromine atoms generated in the last two steps finally combine to give the bromine molecule. The cyclic process has been represented as figure in this slide. The reaction proceeds with the wavelength of light less than 511 nanometer. The rate of formation of hydrogen bromide is same as that for the thermal reaction. In the expression, however, the term root over K1 Br2 is replaced by the factor Ia power half, that is root over Ia, where Ia is the intensity of light absorbed. That is, bromine atom concentration is preserved by photochemical dissociation of bromine rather than the thermal dissociation. This consequently makes the quantum yield inversely proportional to the square root of intensity, and this quantum yield increases with increase in temperature. The next topic is the photodissociation or photolysis of hydrogen iodide. The photolysis is the chemical breakdown of a compound due to the influence of light or radiation. When hydrogen iodide Hi is irradiated with wavelength below 327 nanometer, the hydrogen and iodine atoms are separated, with the rate of that reaction step being equal to the intensity of light absorbed. In the next two steps, the hydrogen atom generated at step 1 reacts with the remaining amount of hydrogen iodide to give the hydrogen molecule and an iodine atom. Two such iodine atoms combine to finally give the iodine molecule. From reaction kinetics applying the steady state approximation, the rate of disappearance of hydrogen iodide is actually 2 multiplied by the intensity of light absorbed and does not depend on concentration of hydrogen iodide directly. But since according to Br's law, the intensity absorbed depends on concentration, so there is an indirect dependence of rate on concentration of hydrogen iodide. The quantum yield for such a reaction is 2. Now we will look at the energy level diagram for photochemical reaction that is known as the Jablonski diagram. This diagram has several energy levels arranged into columns, as can be seen here, where each column represents a specific spin multiplicity. So S0, T1, S1, S2, S3, they all represent spin multiplicity. What is spin multiplicity? Spin multiplicity of an energy level is defined as 2s plus 1, where s is the total spin angular momentum. The multiplicities 1, 2, 3, 4, 5 are called as singlet, doublet, triplet, quartet and quintet respectively. So this is the foundation of a Jablonski diagram. When each electronic state has several vibronic or vibrational energy state V1, V2, V3, V4, V5, etc. The important transitions that are involved in a Jablonski diagram are fluorescence, phosphorescence, and non-radiative deactivation. What is fluorescence? When a photon transition occurs between states of same spin state, that is from S to S, that is S1 to S0. That is known as fluorescence. But when the spin state of the initial and final energy levels are different, for example from T, that is triplet, to singlet, T1 to S0, that kind of an emission is called phosphorescence. Now the fluorescence is much faster and happens in a very short span of time, but phosphorescence is somewhat longer. The non-radiative deactivation can be internal conversion, which is a radiation-less transition between energy states of same spin state. It can be inter-system crossing, which is a transition between different spin state but radiation-less, and vibrational relaxation, which occurs very quickly and is enhanced by physical contact of excited molecules with other particles. So, if we look again at the Jablonski diagram, we see what constitutes fluorescence, what constitutes phosphorescence, and how there is heat loss to environment. In this slide, I have linked a hyperlink in which you students can directly press Ctrl and click at the last word, and you will be led to open. As you can see, you will be led to open another tab in your browser, which will help you to understand what is Jablonski diagram and how it can vary. As you can see here, it is a tutorial where they show how the electrons are how the photons are excited and how they lose energy, and what process is known as what. This is vibrational relaxation, this is fluorescence. Again, vibrational relaxation. Let's see it once again. This is excitation, vibrational relaxation, internal conversion, vibrational relaxation. Here is fluorescence. Here, if you change from fluorescence to say phosphorescence emission and then start, you see excitation, there is vibrational relaxation, internal conversion, vibrational relaxation. Here goes intersystem crossing, vibrational relaxation, and here comes phosphorescence. So you can open this website from the hyperlink and read more thoroughly about the Jablonski diagram and what process indicates what. Let us continue with the presentation. What are the time scales of the processes that are involved in Jablonski diagram? There is absorption, that is in the range of 10 to the power minus 15 second, and it is a radiative process. There is internal conversion. Here you see the violet one is absorbance. The internal conversion is this green one, where the time scale is 10 to the power minus 14 to 10 to the power minus 11 second, and it is a non-radiative process. That means no radiations are released. The next one is the vibrational relaxation. You see the blue part, this is the vibrational relaxation in the time range 10 to the power minus 14 to 10 to the power minus 11 seconds, which is a non-radiative process. There is fluorescence. It is not shown here, but fluorescence is from S1 to S0 is fluorescence, where time range is 10 to the power minus 9 to 10 to the power minus 7 seconds, which is a radiative process. There is intersystem crossing. The brown part, intersystem crossing, which is a non-radiative process in the time range of 10 to the power minus 8 to 10 to the power minus 3 seconds. And finally, the phosphorescence in the time range of 10 to the power minus 4 to 10 to the power minus 1 second, which is the longest of all the processes that are involved. And it is a radiative process. So with this, we conclude this presentation. If you have any doubts, please mail me, or you can also send me your doubts in WhatsApp. I shall be available there. Thank you for your attention.